Goodness a fit, in fact. We're looking at how well a best fit line and its resulting equation works as a predictor. And so we're going to introduce the idea of r, lowercase r, and r squared, usually written as an uppercase. And they're on about how well our linear regression equation fits our data. Alright, linear regression, we're looking at straight line models. Now, if you haven't looked at least squares and linear regression yet, you've gone too far. You need to go back to some of my earlier videos and find out what least squares regression, linear regression, what that means. It's an efficient way of getting a prediction line. Alright, it's usually used with technology, as we will see in this video. We're also looking very similarly at how reliable will my predictions be. See, predictions are one of the most important things or purposes we can do with trend lines or regression lines. Okay, it's often our whole purpose for doing them, so wake up and learn it. Now, the first one that I've mentioned, lowercase r, it's called the correlation coefficient, and you'll find it goes down to -1 inclusive and up to 1. Alright, and it can be any real number in that range there, and it indicates how well a linear regression equation, and in fact its line of course as well, does it truly represent the data being examined. Okay, it tells how well it's possible to put it on a scale like here and we've got r. You can see if we start at 0, it's basically random swarm of flies. If we did a scatter plot of it, there's no linear association. Alright, now as we climb up to the positive values, you've got a positive association between the independent and dependent variables, and as we go up, 1 is a perfect correlation. Okay, so something that's above 0.75, above 0.8, and so on is fairly strong. Now we can have negative association, so as the independent variable goes up, the dependent variable goes down. Alright, so maybe like that, or roughly speaking, that is a negative association. Alright, so if we're looking linear, it might be something like that then. Okay, these are the little axes, okay, little arrowheads. So you know, negative might be what negative doesn't have a negative connotation here. It's just how the pattern works. Alright, and again, if we're near 0, it's very weak or virtually non-existent and goes up to a perfect one at -1. Okay, so in the green zone, okay, the green zone's for loading. That's a joke. If you look in the green zone here, if we have an r value, you know, close to 1 or -1, that's an extremely good fit. In fact, that's pretty much perfect. Okay, so if r is plus or minus 1, if r is close to 0, the model is not a good fit for the data, and the data might be recalcitrant and they don't want a model, or they just might not be a good fit for a linear model. Okay, and so we would say in such a case there's no linear relationship. Usually values lie between, you know, well above 0, but certainly less than 1 in a lot of data sets that we look at school. Okay, now if you want to know what's strong, this is a rule of thumb. Okay, so it's a guideline. 0.8 or above is getting pretty strong, 0.5 or under getting a bit weak there. Okay, and the same works on the negative end of the scale. So a few very convenient indicative shapes there. We have a positive, perfect correlation, strong positive. See, it's got a little bit of deviation there, and yeah, a little bit of variation from a straight line. Definitely positive. You can see some variation, but there's more deviation or variation from some straight line that we could try and draw. That's a swarm of flies, so no correlation, and the same works with the negatives. Okay, from weak, strong to perfect. Alright, let's look at r squared now. The second of two that we're looking at just these two. This is the second one. R squared is called the coefficient of determination. So the first one is called the correlation coefficient. This is called the coefficient of determination. And it's a statistical measure about how close the data are to the fitted regression line. So that's quite similar to lowercase r in its purpose, right? Very similar. R squared is related to the percentage of the dependent variable variation that is explained by a linear model. Now that's probably, for what this video is pitched at, that's probably a little bit too tough there to understand, and so I don't really require you, if you're around about year 10, to understand that. But basically it's this R-squared thing is linked to basically how many of, well, you know what a dependent variable is, how many of these dependent variable values on the x-axis can be explained, or their variation I should say, can be explained by a linear model. So how well does a linear model explain it? Okay, look, if you don't understand that, that's just there for a little bit of formality. Okay, but and I also wanted to show that it's not exactly the same as lowercase r, even though its role can be very similar. What you do need to know, however, is the R-squared, alright, has a different range. You'll only find it between 0 and 1 inclusive, okay, because it's squared, and so when you square something it's going to be from 0 upwards, okay, it can't be negative. So from 0 to 1, or if, as a percentage from 0 to 100%, but usually it's written as a coefficient, meaning in this case a decimal value from 0 through to 1. So you might get 1 of 0.05, for example. That would be reasonably strong. So we don't say positive or negative with R-squared. Okay, and the good thing about R-squared, it's commonly used in nonlinear situations as well, whereas R tends to be, in its raw form, tends to be something that we just find in linear cases only, unless we do what's called a transformation, and that's a bit too hard for this video. Okay, so what's a good one for an R-squared? It does depend a lot on the context. Okay, it depends whether you're looking at humanities or you're depending on looking at a scientific type study or whatever. So it does depend a lot, but as a rule of thumb, another guideline, just use those values that I just showed you with lowercase r just a moment ago. So for example, something of 0.9 is strong. Okay, if something is 0.985, that's very strong. If something is 0.51, that's not strong. Okay, it's not very good, and you'd have less confidence with that. If something was 0.21, that's pretty weak. Okay, so it depends on the context. Like one of my recent videos, we're going to look at two examples using two bits of technology, the first one being Microsoft Excel and the second one being the TI-Nspire. We have here some data points, and what are there? There's 23 people were asked to put down the age of their mum and the age of their dad, alright, in years, and we're going to work out if there's some correlation with it. Okay, so we're going to use technology to find R and R squared through least squares regression. Alright, so some of this is similar to a recent video I did, and if we go using Microsoft Excel and we click on Insert and Insert Scatter XY. Alright, so click on that, and I'm just going for a regular scatter at first, and then I'm going to a quick layout number 9 on this version of Excel that I'm using, but you can see there, you can pause it, and they're the things it's got. Okay, and basically I've shown the finer points of this in some of my other videos, but we've got what we have here. The important things for this video here are your linear equation, but most important of all is the R squared value. Alright, now you can fuss around with this and put chart titles and axis titles, and obviously you could change the scaling. I've shown all that before, so don't bother me now with that, because you need to make sure you've watched my earlier video on that. Okay, go and have a look on the playlist. So the R squared value for this is 0.885, indicating pretty healthy correlation there. And you know, even if you zoomed in a bit, you can see there's a fairly strong correlation with the scatter plots above and below the trend line. You can just see there. Okay, so it would be a good idea to cue in a bit, zoom in a bit on that one. Okay, now how do you find R, the correlation coefficient? Alright, so you've got, like I might have shown it, and actually I did show in a previous video, you can go, one way of doing that is to go equals correl, okay, and open brackets, and array 1 is basically in column A. There you can see all the ages of the various mothers, and so we've got to put the cell references in there. So that goes from A2 down to, which we use a colon for, A24. A2 down to A24. And then you can see the syntax says comma array 2. So that's going to be Dad's ages from, we got B2, colon B24. Okay. Voila, and we've got 0.94 again, also suggesting a positive. Alright, now the thing about R, it tells you whether it's positive or negative. You can see as we go from left to right, it is a rising line for positive gradient of 1.03. So we have a good correlation, it's positive, it's quite good, it's quite strong, it's positive. How do we do that on the TI-Nspire? Well, I've called column A mum and column B dad, and I've put that data in as before, and basically you can add a statistics graph, which is data and statistics, the pink icon, and it will give you this here, provided you go into analyze by hitting the menu and hit regression, and I would choose the linear mx plus b, and r squared it tends to pop up at the same time. Alright, and again we get the same value as we did 0.8845. Alright, oh, where have I lost? There you go, 0.8845, and that's the same as what we had with Excel. Okay, I'm not going to edit out that slight blooper. We've got here the same equation as well. Alright, so that's how we do that part, and to get R you can actually insert here when you go back to the table, spreadsheet table, stat calculations, and you can see linear regression. Okay, and that will insert these values that you see in there. Alright, it's got an R squared value of 0.9408. Okay, and again it's got the R squared value, so it's got all those things there. Just added the R value there. Okay, and of course that matches the R value we had over here. One last example now. We're going to look at fish. Alright, now we have here the blue rectangle explains what we're doing. So fish, at this fish market, get a rating. It goes from 0 to 10. 0 is great, 10 is very poor. Okay, and the price per kilo depends on the rating that Fishman gives it. Okay, so you can see some data there in the two columns. Okay, now I might delete that and pretend I haven't got that there, and basically we'll go through those steps again. We're going to insert, and we're going to insert a scatter plot, and we're going to get actually we're going to highlight the data first. Is actually a better way to go. So we're going to highlight all the data we wish to use. Lovely, and there we go. Now I'm going to click insert, and I'm going to click in scatter, and then I'm going to go to a quick layout and choose number 9. Okay, and we got those same values there as we had last time. Alright, and pump that up, and that's our R squared. And remember, Coral will do what we did last time. Alright, and we got A6 down to A20, A6 colon A20, okay, and then we go colon B6 down to B20, B6 down to B20, and there we go. So it's a negative correlation, this one, and it's strong. Alright, so negative 0.89 approximately, and we can see the gradient is negative, and there's a reasonably good correlation there above and below. There is some deviation, right? But it's reasonably good. So this one shows that it's negative. R squared also indicates that it's reasonably strong around the 0.8, not super strong. Okay, so let's do the last bit now on the TI-Nspire. one of the things we can do is a stat test, or stat calculation I should say, and the linear regression stuff, because this will give us the correlation coefficient R, and we want to make sure we pick the correct things here. So the rating is independent and the price per kilo is dependent on that, and that's there, and we can see some of those same values from before. We've got R at negative 0.89, which we saw before, okay, and that's it there, and R squared of 7915, alright, there, okay. And one last thing we can do is basically add in z-graph, if you want to see z-graph, and we've got the rating is independent, price per kilo, alright, we can see that's a different shape there, and if you like, as icing on the cake, Z can have regression and mx plus b, voila, and R squared there. Au revoir.